Afternoon, everyone. I kindly welcome you all to the webinar on Understanding the Universe using Mathematics, organized by Department of Applied Sciences and University. Today we have the presence of Dr. Pash Shah Sir, Assistant Professor from Vellore Institute of Technology, AP University. I welcome you, sir. Dr. Pasha Sir has recently received his PhD degree with a thesis titled Study on Various Cosmological Models Using Dynamical Systems from Department of Mathematics, BITS, Pilani. He was gold medalist in Masters in Mathematics 2015 at Sardar Vallabhbhai National Institute of Technology. In 2013, he had been awarded Indian Academy of Science Fellowship. He is also an awardee of DAD Fellowship under the category of Working Internships in Science and Engineering. In 2016, he was selected as Inspire Fellow under Department of Science and Technology, Government of India. Sir had secured All India rank 87 in UGC NET exam in mathematical science conducted in June 2017. Also, he has been selected for American Mathematical Society Award to attend the joint mathematics meeting in Denver and also as a Raman Chapak Fellow to work in astroparticle at Cosmology in University of Paris. His area of interest are modified theories of gravity, cosmology, and statistics. He has also keen knowledge about basic origin, Fortran, Python, intermediate C, LaTeX, MATLAB, and Mathematica. He has all his publications in international Scopus Index journals and has presented research papers in international conferences. So, I kindly invite you as a speaker for today's webinar. Please, sir.
Mm. Thank you very much, madam, for your kind introduction. And I'm very happy and very glad to be presenting at the Parul University in this webinar. So I'll begin. So topic for today is understanding the universe using mathematics. Universe, cosmology, astronomy, solar physics, many of these things are actually comes under physics, and we have been all studying in such a way that these courses are of physics. But when I started learning it, I'll just give some history about how I developed interest in astronomy and then slowly towards cosmology, and then I'll begin with my talk. So in 2013, I studied some courses related to astronomy, and I came across some Newton's law, Kepler's law, and some related to Hubble's law. So those things, when it came to me, and then I understood that yes, there is a lot of mathematics in all these things. And then slowly I started doing some internships. I started attending some workshops, and then I got to know that yes, these things have actually a lot of mathematics, and these things actually mathematicians can do very well. Yes, physicists can do it very nicely, and physicists will be there to help us in all the ways. And throughout my career, physicists have been helping me to solve various problems, and but mathematics is lying beneath everything. And especially for this our universe, there are so many things, so many concepts, and actually it's like I feel that actually there is no subject which we are learning as a part of BTech or MSc which is not used in cosmology. So that is what I have this today. This talk is a very general talk. I'll just give you a, a brief first, like a first layered introduction, that how in a very basic differential equations we can use and understand some magic of how universe is evolved and how it is evolving currently. So that is how I developed interest, and I am sure that with this talk it will be helpful for others also to relate these things and work in this area. Yes. So this is the overview of my talk. I'll begin with the definition of what is cosmology. I'll I'll discuss what is cosmological principle, what observational evidences we have for universe, what are the basic fundamental particles of our universe. And so this will be the introduction part. Then we'll move to the geometry of the universe. There the mathematics is coming into picture, and then we'll see some simple cosmological models, how we can interpret them using mathematics. And then in some concluding remarks, I'll pose some questions, I'll pose some theories which on which we can have a discussion. Yes, and any point of time, if any doubt is coming, please stop me at that point itself, or you can stop at you can ask at the end also. There is no problem. Yes. So what is cosmology basically? So cosmology is nothing but it is a branch of science. It is concerned with the study of chronology of the universe. Now chronology means like we are studying what happened in the beginning, what happened in the intermediate state, what is happening now, and what will happen in the future. So like from big bang, this is one term, big bang it basically means the initial explosion which happened in our universe. That is what is widely believed to be the beginning point of our universe. So this is what separates astronomy and cosmology. So cosmology is basically the study of the entire universe. Astronomy is basically for a like when we are studying about our solar system or our galaxy. So those studies comes under astronomy part, but cosmology is basically we are taking group of galaxies, we are looking into trillions of years back, right? Those things when we are doing, that is that comes under cosmology, whether it is in terms of distance, whether it is in terms of time. When it is very large, it comes under cosmology. So that is why the next line is saying that it is a study of the large scale structures and the dynamics of the universe, how the universe is changing, right? We all know that universe was not the same as we are looking now, right? Everything has come from something, okay, and everywhere you would have heard the term of God particle. So from where everything has come, that study is basically cosmology. So how dynamics of the universe have changed, how things have evolved over a period of time. So there was one small dot, which Big Bang is called one small dot. So from that dot, everything which we see around here, sun, our solar system, our Milky Way galaxy, we ourselves, right? All these things, water, everything has come from that one point. Okay, so from where it has all come, that is the basically study of cosmology, and its primary scope is to understand the origin, evolution, and the future of the universe. So this is what a very nice picture which is showing the evolution of how the universe is started. You can see in the left hand side a very bright light spot. This is nothing but the said as the Big Bang. And then near to that you can see an inflation word. Inflation is basically exponential expansion which happened for for a very short duration, 10 to the power minus 36 seconds. Okay, we'll not get into the details of how these numbers are coming. We'll just first get the essence of what how our universe is made. And then there is something known as the afterglow pattern. So there is some a mark of 3,75,000 years. Okay, so before those things we are not able to see. That is where our cosmic microwave background is coming, from where actually till that point we have all the data, so we can see till that past. Okay, and then some dark ages were there, and then slowly the developments of galaxies, planets, etc. have started, and then towards the end there is some dark energy accelerated expansion. So it is considered that universe is having two acceleration phase. The first acceleration phase was during inflation period, which was at the very beginning, just after Big Bang, and the second accelerated expansion is coming towards the in the recent times. Okay, and the total expansion phase, as you can see in the below timeline, it is some 13.7 billion years. So that much time it has taken from the initial explosion till now, and so many things have changed. Our entire dimensions and entirely the way it looked, everything has changed. And this is not even 1% of what we till now know. Okay, there are many things which are yet to be explored. There are many open problems in the universe. Actually, this topic has the most number of open problems in the in all topics. So next is what is a cosmological principle. So what did cosmologists do in the beginning? So these things were not known from the beginning, like what the picture which we saw in the previous slide. This was not known from the beginning. So what was done is, so this cosmological principle was formed. This principle is, so some set of rules were formed. So based on this set of rules, we started our calculations. So the main motivation of the modern cosmology is to believe that we do not occupy any special place in the universe, right? So some Greek philosophers in the beginning, towards 4th century BC, they used to believe that Earth is at the center. Then there were some, so that is called an Earth-centric universe. Then there was some sun-centric universe which was formed. Some models were formed. That model said that sun is at the center. Everything around is moving around the sun. Now those things were there, but recent observations before 1 century, everything was clear that uh, we do not occupy any special place in the universe. We are just like any other particle. Okay, Earth is like any other particle in the universe. So we have the term that Earth is the universe is homogeneous and isotropic. Now these two do not imply each other. These two have a different meaning. What is homogeneous? Homogeneous means that universe is looking the same at every point. So homogeneous means universe is looking the same at each and every point. And what is isotropic meaning? Isotropic means that it is looking same in all direction. Okay, this two looks very same, but it is different. So I'll show you one example where you can understand that yes, one of them. So since universe is both, so we are not able to understand. But if any diagram is having only one property, then I think it will be very clear. So I have one diagram. I'll show you. Yes. So see the picture first here. So picture one is homogeneous. It looks same in all directions, in on all locations, but it is not isotropic. Okay, it is not looking same in all the directions. So if you see in vertical direction, it is different. In horizontal direction, it is different. All tiles are aligned in the horizontal direction. Tiles are not vertically aligned. So it is looking same in all the location, but not in all directions. So that is not isotropic, but it is homogeneous. We see the second figure. Second figure is looking same in all the directions, but it is not same in all locations. So for every location it is different, but in every direction it is same. So it is like from a circle, it is just all rays are coming out. So that kind of figure are normally isotropic but not homogeneous, and this tile figure is homogeneous but it is not isotropic. So these two are not same. They looks like a bit similar, but these two are different things. Now why do we need this? We need this because some mathematical equations when we are trying to make, we should have certain observations. Now some may ask a question that, sir, whether this is true. So because you can see that if we take solar system, so if you see the diagram of solar system, there is Mercury, there is Venus, there is Earth, there is Mars, then there is some gap in between, there is an asteroid belt. Homogeneous is large and small. I've thought to put some numbers, but since that numbers will not be able to remember and all, it will be very difficult. But we can understand in that sense that for cosmology, even our Milky Way galaxy is small. Okay, we can think in that manner. Okay, so our Milky Way galaxy is also not homogeneous and isotropic. Even a group of 5-6 galaxies, okay, that is also not homogeneous and isotropic. For cosmology, when we say large scale means galaxy clusters, collections of 10, 100,000 galaxies like that. That is homogeneous and isotropic. So the second line is only true at large distances. Then what observational evidences we have? Till now we have done a lot of observation. You may have seen that there are a lot of uh, uh, research going on for observation. There are a lot of NASA projects and ISRO projects are going on for observation. So what we have obtained till now. So the most important observational evidence in cosmology is that everything in the universe is moving away from us. So whenever we are seeing anything, it is looking like it is going away from us. Okay, so that gave us one idea that in the distant past means very long time ago, everything in the universe was very close. And if we trace our history very far, everything is coming together, and that is called the Big Bang. So that we saw one figure. So that figure is actually coming because of this very important observational evidence, and that evidence is saying that currently everything is moving away from us. So there was some past where everything is together, and because of this the Big Bang happened. Now this is not the only observation, but this is one of the important prominent observation. Now we know that since everything is moving away, so if an object is very far, its motion will also be very rapid. Its recession will be more rapid. Okay, so this was systematically used and applied by Edwin Hubble. This was one of the great cosmologists. In 1920, he did this and he formulated what is called the Hubble's law, and he gave that velocity of recession is proportional to the distance of the object from us. So V is equals to h naught r. H naught is the proportionality constant for Hubble. This is the relation he gave. So he studied for various galaxies. So this you can see in the left hand side, sorry, in the y-axis there is a distance, and in the x-axis there are velocities, and we can see that there is a straight line, almost a straight line formation is there. Is a linear relation. You can see this is a linear relation. V is equals to h naught r. A simple, straightforward linear relation. We put V, we get some r. Okay, for some velocity we get some distance. Okay, and if we have enough data, for velocity and distance, we get a rough estimate of what can be h naught. Got it? How we do? So these are observations, and from observations we get the values of velocity and distance. From that we get the h naught. Okay, so these were some of the very prominent observations which were made for our universe. Then we move to what are different particles of the universe. So what kind of particles are universe made of, and what is each particle's contribution, right? So everything is made up of the fundamental particle, and the behavior of the universe is depending on that. Those properties depends on the properties of these particles. Okay, so everything is made up of these fundamental particles, and we are all made of atoms. Atoms is basically mass contribution is due to proton and neutron. There will be electrons in the orbit. Electrons is having a very negligible mass, and now these atoms, recently in more fundamental physics, we have gone to a term which is known as quarks. So these atoms are actually made of, these protons and neutrons are actually made up of quarks. So each proton is made of 3 quarks. Each neutron is also made of 3 quarks. So if you have learned some, so I think in 11th and 12th we have gone through these things, that protons and neutrons have approximately the same mass. So each of them is made of 3 quarks. And the general term for particles made of 3 quarks is called baryons. So in cosmology, this baryons term is very much used. And baryons is basically nothing but any general particle which is made of 3 quarks is called a baryon. So whatever we see around us, our Earth, our solar system, our galaxy, so all the proton and neutron particles, they are all coming under baryon. It is called the normal matter which we have. Okay, that is called baryon. And then we have another quantity. So this quantity is known as a radiation. So radiation are also some individual particles, and they are actually the packets of energy. They are carrying some energy. Why they are carrying energy? They are carrying energy because of their speed. Radiation is not static. Radiation will be traveling across, and that is why it will have some packets of energy. It will transfer energy, and it is referred as photons. That was proton. This is photon. And it can interact with baryons and electrons, and whenever a radiation is interacting with baryon, it knocks out the electron from the atom. That process is known as ionization, and it scatters off free electrons. So whenever any free electron is there in an atom, it will scatter off that. That is known as the Thomson effect. And more energetic photon, more energetic photon, what does it mean? It means that with more speed, when kinetic energy is there. How kinetic energy is defined? Half mv square. So when velocity is more, the energy will be more. So more energetic photon will have more devastating effect on the particles. So knocking out of an electron or doing scattering effect, so those things will be more devastating if photon is having more energy. So these two imply each other. So till now we have seen two particles. First is the baryons, that are the matter which we in general see. The second is the radiation with the light, basically the energy source is dark energy. So as I said in the beginning, let me go back to that fundamental basic picture which I showed you in the beginning. So this picture you see at the end, there is something known as dark energy accelerated expansion. So we may wonder what is dark energy, how it is coming, from where we got that dark energy is there in the universe, and these kind of questions are there, and still till now also the correct version of how dark energy is, whether there is a dark energy or not, so those type of questions are still there. They are still the open problems. There are many theories which study about these dark energies, and there are few other theories which says that there is actually no dark energy in the universe, so there is some fundamental mistake in the calculations and dark energy is not existing. So we first before going into all those things, first we'll understand what is dark energy, and then I'll try to show you that how dark energy is coming into picture. It's not that some calculation mistake is made. So we'll see how dark energy is actually affecting our universe. So that is actually the correct thing, that how it is affecting our universe. So why we want to include that dark energy, why we want to have our dark energy term in the universe. So that is very important. So let us see that. Yes. So with the assumption of Big Bang theory, it was expected that the universe is undergoing deceleration currently. So this was obvious. Why this was obvious? Because when we observe that there is a Big Bang, then everything is going like there is matter formation, there is this galaxies formation, star formation is there. Now we have from the beginning we have studied about Newton's law. Newton's law. What does Newton's law say? Newton's law is saying that whenever there is a gravity, gravity will pull things, and we will get into closed environment. Correct. That is what we have studied, and that is what observations. That is what scientists also believe, that our universe might be going through a deceleration phase. Deceleration phase means that there was some energy in the beginning. Due to that energy, universe expanded. But now, since so many things are there, now because of this, our uh, gravitational pull is actually closing everything together. Now there is one big galaxy in our neighborhood, and Milky Way galaxy is also there. So it was believed that these two galaxies are having some gravitational pull, and they may be interacting, and they may come closer to each other. But there's a very surprising thing in 1998 and 1999, with two separate experiments by Reis and Permutal. They were awarded with the Nobel Prize, and it was proved that the expansion of the universe is actually accelerating. Now, this is where things changed tremendously, because till now everything it was very clear that yes, universe is decelerating, we are going, so then Big Bang happened, everything expanded, now we are again going back to original point. That is what it was believed. 1998 and 1999, this thing changed tremendously, and we arrived at the conclusion that universe is actually accelerating. Now, what what things did it change? Now, this led to a belief that there must be some other cosmological fluid which is yet to be observed experimentally. It still is, but it allowed the universe to accelerate in late time. Now, this quantity was called dark energy. So, what do? We say that we could we observe baryons. Now, baryons is having gravitational pull. So, in our universe, whatever we observe through telescope or through naked eye, we see that these are all normal matter. Normal matter is having gravitational pull, so they should have a deceleration, but it is not there. So some other kind of fluid is there, a cosmological fluid. So some other kind of material is there which is having the reverse gravity reaction. Okay, what do I mean by reverse gravity reaction? It means that there is some something, some other properties there, in such a way that it is having a influence that universe can expand in late times. Okay, so this quantity was called dark energy, and dark energy does not interact with any observable materials, and it does not obey the existing gravitational influence. Okay, and see what happened is actually, uh, so universe, they believed that universe was expanding, but they were thinking that it is a deceleration expansion. So there are two things here. See, something is expanding, but that rate of expansion is decreasing, so that is some different thing. And there is something is expanding, and that rate of expansion is also increasing. Okay, these are two things. We have to understand that this is second derivative. You think it as in terms of second derivative. Acceleration is a second derivative. Now, second derivative is greater than zero, second derivative is less than zero. Think in that term. So expansion is there, but decelerated expansion means what? That the rate of expansion is actually decreasing. Okay, that is what was believed. And now it was proved in 98 and 99 that yes, expansion is there. That is correct. But that expansion is accelerated expansion. Means what do I mean by that? Suppose in 10 years, whatever expansion is there, in the next 10 years, that expansion will be even more. And in next 10 years, even more. So that is what I mean by accelerated expansion. So it was not that there was no, it was not believed that there is no expansion. It was believed that expansion is there, but decelerated expansion was believed. But now it was proved in other way. So what does dark energy do? So dark energy does not interact with any observable objects which we see. Whatever we are seeing around us, dark energy does not interact with them. So there is no gravitational pull or gravitational influence because of dark energy. So if dark energy is sitting around anywhere, so there is no gravitational influence because of dark energy. So that is what how it behaves. Then there is one more term which is known as the dark matter. So dark matter is also a similar concept that also we cannot see, but the main difference between dark energy and dark matter is that dark matter has clustering properties. Clustering property means that it can have it is having a gravitational pull. Okay, that property is there, but still it is not visible to us. And why it is added? So it was added because of some observational predictions of galaxies and galaxy clusters did not match with what Newtonian gravity was suggesting. So some extra mass was required to match the observational data, but we were not able to detect anything in the electromagnetic spectrum. So these electromagnetic spectrums are basically our devices to observe things in the universe. So these dark matters, there was some material which was not observed, but we could feel that there is some extra mass present there, such that the observational data is matched, but that was not observed in any spectrum. So because of that, dark matter was also formed, and so definitely it is satisfying the clustering properties. That is how it separates from dark energy. So it behaves similar to what is called the pressureless dust particles. What is pressureless dust particles? It is same as baryons. Okay, we discussed about baryons. That is photons plus neutrons. So that is pressureless dust particles. I'll come to why it is called pressureless. So in a bit. Then we have this kind of an image which says that how the distribution is done in the universe. So we can see that there is a 75% dark energy. This is not exact numbers, but rough estimates are there that 1/3 of a universe is entirely of dark energy. 1/5 of the universe is dark matter. So that leaves only 4%. That is you and me. Okay, that only 4% is what we actually observe, what we see. All the galaxies, all the solar system, everything, moon, earth, everything is there in that 4%. Rest 96% we are not able to see in any electromagnetic devices, electromagnetic spectrum. Okay, so how these things come? So we have one more concept which is known as the co-moving coordinates. So these co-moving coordinates are nothing but they are carried with the expansion. And for a uniform expansion, we can write it in this form: r is equals to a of t times x, and r is the physical distance, x is the co-moving coordinate. And this a of t term is very important. A of t is actually only a function of time t, and is called the scale factor of the universe. It governs how expansion of the universe will take place. So in the next slide, it will be clear that why we are using these coordinates. So you can see here, co-moving coordinates are used in this manner. So it is taking care of what expansion is happening. Okay, so you can see in time t0, the universe was a bit shorter, and you can see in the time t1 that universe has expanded. So x and y here are co-moving coordinates. Okay, so that is how this co-moving coordinates are coming into picture, and the relation is like this: r is equal to a of t times x, and r is the actual physical distance, and x is called the co-moving distance. So it will take care of the expansion. Whatever expansion will be there, x will still be same. Okay, then we come to Friedman's equation. Now this looks like a big jump, that uh, why we are discussing about this Friedman's equation. So Friedman's equation are actually coming from Einstein's tensor, Einstein's equation. Now, for that, we need to understand what are tensors first, what are manifolds. So we will not go into there. What we are doing is, from that we are extracting this Friedman's equation. These are coming from Einstein tensors, and we are taking some components from that, and based on those components we get some different equations. So for us, these equations are very important. As a mathematicians, we have to look at these equations and understand what information is this equation hiding behind it. Okay, so these Friedman's equation are actually, now for this equation, to get these equations we require cosmological principle. So we need to apply the condition that universe is homogeneous and isotropic. Only then we can get these equations. So that's why that we discussed in the beginning, cosmological principle, homogeneous, isotropic. Now why these things are required? These things are required so that we can write the Friedman's equation in the way it is written here in this equation. Okay, now it looks a very simple equation, and yes, definitely it is a very simple equation, just a first order differential equation with a degree 2. Very simple equation, only a dot square is present. But how it is helping? It is helping in a way that we can understand the geometry of the universe from here, and we can also say something about the density. So we'll see what all terms. So terms, I'll just tell you what are the terms. A is the scale factor. Dot is the derivative with respect to time. G is the gravitational constant. Uh, Rho is the density, and K is the geometry of the universe. It is called the curvature. So expanding universe always has a constant value of K, which remains throughout the evaluation. So K is actually constant here in the equation. Now it depends on what our universe is, whether our universe is flat, whether our universe is open, whether our universe is closed. So based on that, we need to put the value. So this is how these are the three figures we can see. The first figure is a closed universe. The second figure is an open universe. Third figure is the below one is the flat universe. And how we can identify? We can identify it using, we can place any triangle. If it is a flat universe, triangle, all the three angles summation will be 180. For a sphere, that angle summation will be more than 180. The closed universe, and in the open universe, you can see that the summation of all the three angles will be less than 180 degrees. So that is how we get the idea. Okay, and what how we take the basic cosmological models, we take it as a flat universe. So for flat universe, we substitute this K as 0. Okay. And using Friedman's equation, we arrive at a different equation, which is known as the Rai-Chaudhuri's equation. This Rai-Chaudhuri's equation, you can see this is based on the second derivative of A. A double dot is there. And this equation gives the condition for accelerating and decelerating universe depending on the sign of A double dot. So whatever be the sign of A double dot, based on that we can get the information about acceleration and accelerating and decelerating universe. We don't need to solve it first. We can understand by the sign that whether our so what happens when a universe is accelerating, what happens when a universe is decelerating. So, and we have one more relation between P and rho. P is nothing but the pressure, and rho is nothing but the density. So this relation is a linear relation, and we have P is equals to omega rho C square. C is nothing but the speed of light, 3 into 10 to the power 8 meter per second square. This is generally known as equation of state. And in specifying the pressure, we are saying that what kind of material our model universe is filled with. So we'll as you would have seen in the overview, at last I said that there will be some basic cosmological models we'll discuss. So when we are specifying the pressure, we are actually saying that what kind of material our universe is made up of. Okay, whether it is of baryons, whether it is having some radiations, whether it is having dark energy. So those things we can study with this. Now, if we see this equation, if we see this Rai-Chaudhuri's equation, so we can look carefully at the right hand side. Right hand side, we can see there is a term of rho plus 3p. Right, there is a term for rho plus 3p is there, and on the left hand side we can see that there is a double dot term present. So if we look at that carefully, so we can note that rho plus 3p, when it is greater than 0, the universe is decelerating, and when, because there is a double dot negative sign is coming, and I made one mistake. And when rho plus 3p is less than 0, the universe is accelerating. Okay, this second line, it should be lesser than 0. I made a mistake. Here it should be less than, sorry. In the second line, it should be lesser than 0. Now, this condition could also be looked at in terms of equation of state parameter. So here we have defined this omega is the equation of state parameter. So we can study in that terms also. So we can say that whenever omega is greater than minus 1 by 3, there is a deceleration, and whenever omega is less than minus 1 by 3, there is an acceleration. Okay, but what happens when whatever universe we are observing, whatever things we are seeing around, all is having omega between 0 and 1 by 3, positive 0 and positive 1 by 3. We are not having anything in the negative side. Correct. Now, but what does this equation is saying? Omega is lesser than minus 1 by 3. This is required. So some materials with omega lesser than minus 1 by 3, that is required for acceleration. Okay, so how do we get that? We get that from dark energy. So dark energy is such a material which is believed that it is having omega in negative. Okay, and then from Rai-Chaudhury's equation, we can do some calculation and we obtain the following equation. This is known as the fluid equation. So this fluid equation is basically nothing but it tells about how density of the universe is evolving with time. Evolving means how it is developing or changing with time. And here the first term is about the, you can say that rho dot term is there. So it is about dilution of the density, and second term is about the work done by the pressure. So this is the fluid equation, which is coming from combinedly from Friedman's equation and the Rai-Chaudhury's equation. And some basic cosmological models, if we pick, we can pick a very basic model which is only based formed with matter. So for matter, there is very negligible pressure, and we take P is equals to 0. So pressureless universe is very simple model to consider our universe. Means we are saying that entire universe is only filled with just the pressureless matter. Okay, so why it is a good approximation? It is good approximation because once all the atoms have cooled down. Now you imagine the Big Bang when it happened, it was everything were very hot because of the energy and then photons. So when everything is cooled down, uh, as they are quite well separated, and also for collection of galaxies. So for collection of all the galaxies, a pressureless universe is a very good example for understanding. Now, since we have learned about dark energy, we know that this is in general it is not true. But what do we do here? We take that a pressureless universe. We take that entire universe is pressureless, and we study some properties. Then we consider that entire universe is only radiation based. We study some properties. Then we combine them. Okay, that is how universe models are building. Slowly and slowly we move step by step. Okay, we cannot say that okay, this is wrong, so let us not do this. No, we'll start with this kind of a model. We'll see what problem is coming, then we change accordingly, that okay, this is the problem coming, so let us change our argument, or let us change the way we were dealing with the problem. And similarly for radiation, this relation is like this. So for matter, I said that P is equals to 0, this term is coming. And similarly for radiation, what are radiation? First, which particles which are moving at speed which is close to speed of light. And here I had written one term which is non-relativistic. So whenever I say non-relativistic means the speed is very less compared to the speed of light. Okay, if I'm going by a car, I cannot say that my speed is this much percentage of the speed of light. Okay, because that is very less, that will be very less speed, so it will be hardly 50 kilometers per hour, 60 kilometers per hour, so that cannot be compared with the speed of light. So such speeds are known as non-relativistic speed, and whenever the speed is comparable to the speed of light, then that kind of particle will be radiations. Okay, we cannot travel at that speed, only radiation can travel, and that kinetic energy is there, half mv square, as I said. Velocity is very large, so their kinetic energy is leading to the pressure, and that pressure is written in this form: P is equals to rho c square by 3. Any particle moving at the speed comparable to speed of light, I put a question mark because I wanted to ask what is the speed of light. I've already said 3 into 10 to the power 8 meter per second square. So at that speed, we have uh, this kind of equation of state. Once we solve this equation, so we had this fluid equation. Now we have the relation between the rho and P. Okay, why we did equation of state? We did equation of state because we have a relation between rho and p. Now, once we have rho and p, this becomes a variable separable form of equation. Just a simple, very basic differential equation. We can solve it, and we get, for a matter, we get rho is proportional to 1 by a to the power 3. So here the density is falling is proportional to the volume of the universe, because a cube is there, so we can consider it in, imagine it as it is falling, because it is 1 upon a cube, so it is falling with the volume of the universe. And when we do for radiation, so rho is proportional to, in this equation, p is equals to rho c square by 3. This we can substitute, and we get rho is proportional to 1 upon a to the power 4. So here also the density is falling, but density falling is more here, means it is more slowly it is falling, because a to the power 4 term is appearing here, and this extra term is coming due to the pressure. So a cube is coming because of the volume, and extra 1 a power 4 is coming because of the pressure which is applied by the kinetic energy of the radiations. So see how we have solved the differential equation. You see, this was a differential equation. Now we don't know what is rho, what is p, but simple models we have considered that let us take p is equals to 0. Okay, so then we solve. Let us take p is equals to some rho c square by 3. So we have got one more model. Now these things, solving this is a mathematical thing, but how do we solve and for which numbers we solve? We are not solving for any general number. We are solving these equations for a very particular numbers, for a very particular uh, terms we are doing it. And why, how these particular terms are selected? These particular terms are selected based on what physics is behind this equation. Okay, so this equation is purely mathematics. The only thing where physics will come, or how, see, I'll have this equation, I know how to solve it. I will not know that what relation I should put between rho and p, because then only it will become variable separable, and then only I can solve. So how we can do that, we have to know from the uh, physics behind the concepts. Okay, and this a dot a is actually nothing but, not worry about this a dot upon a. A dot a is upon a is actually h. So okay, so yes, so this we have done. And then if you want to see more about how this Friedman's equation and equation of state are solved, I'll highly recommend you, please, you can go through, visit this lectures uh, from Caltech University. There are actually, this particular thing is given in the second lecture, but all lectures are very, very good, very fundamental, and it will give a good essence of cosmology terms, and which we can solve and understand. So this is this quite good reference which you can use, and you can understand how, if you have still some doubt is there that still how these things are coming, or how this has been taken, then please visit this lecture. It is a very good exercise, and you can also try and do for some other problems. Okay, so then we can see here how matter dominated universe, how radiation dominated universe are behaving differently. Now, why this behavior is different? What is a matter dominated universe? What is a radiation dominated universe? A matter dominated universe means that the matter content is more. Okay, what do I mean by matter content is more? It means that it is formed. So I'm assuming that there are only two things in my universe. There is no dark energy, no dark matter, nothing is there. Only matter is there, only radiation is there. And if there is a matter domination in the universe, then how the universe will behave? If more than 50% is radiation, then how the universe will behave? Okay, now in reality, these are not the two only things. There are many other things. As I said, and for combining all those things, okay, combining all those materials, we form our universe models, and by that we do the calculations. So yes, now I'll have some closing remarks. Now this will take a lot of time because I have many things to say here. So first, what we did is we did differential equations in cosmology. We saw some differential equations which are there in cosmology very few, one or two equations we saw. We saw Raychaudhury's equation, we saw Friedman's equation, we saw the fluid equation. We solved fluid equation for two particular categories, and we understood that what physical understanding we can get from the differential equation. Now I have a very I have a question that whether we can use linear algebra to study the universe. So how linear algebra, that matrices is there, how eigenvalues, eigenvectors, whether is there anything where we can use this linear algebra to study the universe? The answer is yes. Actually, my work is more related to studying linear algebra in the universe. So I'll just give you one idea that how linear algebra is coming and we can have a very large discussion on how linear algebra is coming. But I'll give you one brief idea. So linear algebra, we are using Jacobian matrix. Now Jacobian matrix is having some that matrix. We can take the Taylor series expansion, we can linearize it, and we can have some eigenvalues. Now those eigenvalues are actually very important in the sense that those eigenvalues signature. Now if all the eigenvalues are negative, we have studied in terms of differential equations that when all these eigenvalues are negative, we get a stable point. That critical point is stable. If all are positive, we get a unstable point, and if some are positive, some are negative, we are saying that it is an saddle point, right? Those things we have studied. Now that is actually very important in cosmology. So to study the various models of the universe, we have certain critical points. Now those critical points, you can say that like a big bang is like a critical point in our universe. If we take some in between point, somewhere when dark energy started, now that becomes our critical point. So we are actually seeing that how we can make that critical point as stable, unstable, right? So that stability will be in the terms that if that point is stable, it means that universe can evolve from that. If that point is unstable, it means that universe will explode from there, right? So in that terms we can study, and there are actually lot of paper and lot of research going on related to this stability and stability analysis. Basically my title of thesis is also based on this dynamic. So the dynamical systems is actually the correct term for this, not linear algebra, but I put linear algebra because it gives the real understanding of what is being used. So dynamical systems are basically two equations which are simultaneously running, and for those two equations we simultaneously not solve it, but we study the stability properties of that equations. So that is what this dynamical systems is doing. Now there are infinite unsolved mysteries of the universe. One of them is from where is dark energy coming? Who is governing this dark energy? Whether dark energy is really there or not, right? Correct. I do not have any answer. Anyone is having no answer for that. So we really don't know whether any energy, any external force is there who is governing this dark energy, how this dark energy is increasing, right? Percentage of dark energy is increasing. So how this is happening, we really do not know. When will the universe end? Will it ever end? We don't know really, because we know till now that yes, universe is expanding, and in last 100 years we have actually made a landmark landmark uh, calculations and landmark theories we have built, and we have come very far, right? What we knew before 100 years, now we have come very far, but still there is a long way to go. So the main questions are these: that when will universe end? Will it ever end or not? Then there is a concept of multiple universe, whether we can have a multiple universe running in parallelly, running simultaneously, and that is called multiverse. So there are theories which believe in these things. So whatever I'm stating here, all there are theories where it is believed that these things are there. Okay, there are theories which believe that there is no dark energy, because they are saying that if dark energy is there, from where it is coming. Okay, then there are theories which believe in multiple universe. And then, is time travel possible? Can we go to past? Okay, so there is a very famous grandfather paradox is there. If I go to my past, if I kill my grandfather, how I have come? Okay, so that is a very famous paradox that which we actually do not have any answer, and so many theorists believe. So these are actually the theoretical concept. Till now, no practical implementation on this. Till now, somewhat it is going, but not in great extent. But this is there, and that many theorists and many other philosophers also believe that traveling to past is not possible, but traveling to future may be possible. We can travel to future and explore some things. Okay, and then how big is our universe? Okay, whether it is the universe is expanding, but whether it is expanding inside some box. So is there some box there? What is the size of that box? Right. So this how big is our universe? How big it can become? Right. So if that box boundaries are touched, it will stop. But whether such boundaries are there or not, whether it is expanding inside something or whether it is just expanding. Okay, so that kind of questions are there. And what is the age of the universe? So exactly, it is believed to be some 13.7 billion years, but whether it is true or not. Okay, and we are considering time to be going in only one direction. Whenever we study anything related to cosmology, we are saying that time is actually in one direction. It is going from Big Bang is like point 0, and currently it is 13.7 billion years. After some years, it will be 14, 15, like that. But there are some theories which believe that time is actually coming around, around in the sense that we have begun at one point, we are going in some direction. So it is like a circular motion is there, and after some years, we'll actually come back to the same point. So that is all. Also, theories are there, and actually, we do not have enough observational evidence or enough theoretical evidence which says that yes, actually, indeed, time traveling is actually sorry, the universe is traveling in a circular manner, and at some point of time, again, we'll start from the beginning, and again that cycle will go on. It's like a cyclic. Yes, cyclic is the correct word. So in the cyclic motion is there. So whether such thing is there or whether time is traveling just in one direction, whether it is just increasing. So those things are still unknown. Still, we are trying to find more on that, and let's hope that we can find more and more interesting things our uh, from the mathematics point of view. We can get best in this subject. These are my references. These are three very good textbooks if you are interested in starting to learn cosmology. The first is Andrew Liddell. It is a very fundamental, very basic book. I recommend all the three books are really very nice. If you want to start learning and understanding about cosmology, you can always refer to these books. There are very good lectures online available in YouTube. You can go through that. It will be helpful. What about my research? As Swapnila madam has already said, my research is on dark energy, dynamical systems, some interaction models of the universe, which are there, and then some modified gravity. So as I just said one term that there are few people who believe that there is no dark energy. So what do they believe? They believe that the gravity which we are considering is actually wrong. There is some modified gravity is there. Some different kind of functions are present, and we can modify that gravity in such a way that we don't require dark energy. So that thing is called modified gravity. So I am doing currently research on these topics. If anyone is interested in some summer project or PhD, you can reach out to me on my email ID at pitap or at gmail, or you can connect to me in LinkedIn as well. And I'll want to end with a very famous quote that a universe is full of magical things, patiently waiting for us, our wits, to grow sharper. So actually, universe is waiting for us to know more and more things. So we are actually exploring, but already these things are discovery. These are not inventions. Already they are existing. We are just discovering. So universe is waiting for us so that we can our minds become sharp enough so that we can understand what is happening in our universe. So with this note, I'll want to end. I want to thank the audience, and I'll if any questions are there, please let me know. Yes, please ask.
Any questions from the attendees? If attendees will have any question, they can reach out to you directly or personally.
Yes.
Thank you so much, sir. I thank you on behalf of Paral University for such a knowledgeable and informative session. Thank you so much, sir, once again.
Yes.
Once
Thank you, madam.
welcome. I really appreciate the quote that you ended with the session. It's really good.
Yes. Yes. And if you felt anything which is means for audience, if anything you felt which was very different or difficult, you can always reach out to me. You can ask me, or some references which I gave. You can look at them, and there are other ways also to look at various things. This is so for cosmology. It is that this is my way of looking at things. There can be several ways of looking at all the things, right? So that always happens. So if more and more, if you are getting interested and if you want to learn, you can always contact me. You can visit all the lectures or any other online material is available. You can always visit that, and you can please ask any doubt is coming. Okay, thank you.
Thank you so much, sir. Thank you everyone for attending the webinar. Thank you once again.
Thank you, ma'am. Can I leave, ma'am?
Yes, sir. We can
Yeah.
end the webinar over here. Thank you everyone.
Yes. Okay, thank you.